In this video, I want to demonstrate some of the properties of this cross product that we've been looking at, as well as a connection with the dot product as well. We know how to calculate dot products. We also know how to calculate cross products. To keep this video short, I'm going to avoid doing those calculations by hand, but instead, I have two little programs that I wrote that will do the calculations for me. In this one, the user is prompted for two arrays that have three slots in them. These will represent vectors u and v in three-dimensional space. In the case where I'm in 2 dimensions, we'll just make the third components 0. Having entered the two vectors, I'll have a little loop that for indexes 1, 2, and 3 adds up as a running sum u number I times v number I, and then I print out to the screen what the dot product is. In this program, the user is prompted for vectors u and v in three-dimensional space. S is not used in this program. It's a leftover from the previous one. We do, though, have a three-dimensional vector called cross. We'll enter u, enter v, and then the three formulas near the middle of the program, these, are what you get when you write out the cross product u cross v in terms of the components of u and v. After that, I print the cross product out to the screen, and that's the end of the program. The first property that I want to demonstrate is that u cross v is always the negative of v cross u. We'll look at several examples of this using my program, and then in the third video, we'll show logically that this is always going to be true. So if I take the vector 1, 2, 3 and the vector 4, 5, 6 and form the cross product, the components of the result is -3, 6, -3. I'm going to run this again, except I'll interchange the order of the vectors. If my claim is true, then I should get 3, -6, 3 instead, the negative of the answer that I previously had. The second vector from the previous example now plays the role of the first one. And the other vector is 1, 2, 3. And as you can see, this is in fact the negative of what we got before. Let's do another example of this. (2.1), 4.3, 5.6, -1.3, 4.7, 7. The cross product is, up to rounding errors, 3.78, -21.98, and 15.46. -1.3, 4.7, 7, 2.1, 4.3, 5.6, and I get the negative of the answer that I had previously. For those of you who are interested in the details of those rounding errors, take Math 4670 and I'll tell you all about it. There is a kind of associative law associated with the cross product. When I have a number, c, if I calculate c times a vector and cross that with another, I get the same result as if I had multiplied C by the second vector first and then formed U cross the result. This is the same as forming the number C multiplied by the number U cross V. As my example, I'm going to let C equal the number 3. U will be the vector with components 1, 2, and 3. V will be the vector with components 4, 0, and 1. In my comparison here, I'm going to need to know what C times U is. C times V. I'll use my program to calculate this cross product and that cross product, as well as that one. C times U is 369. C times V is 1203. I'll calculate U cross V using my program. Now that I know the cross product of U and V, 3 times U cross V is 6, 33, negative 24. By way of comparison, the number C times vector U cross product with vector V is 3, 6, 9. Cross product with V, which is 4, 0, 1. Which again is 6, 33, negative 24. And likewise, if I want to calculate U cross the vector C times V, this will be vector 1, 2, 3 cross product with 12, 0, 3, which again is 6, 33, negative 24. So this supports the claim that CU cross V, U cross with CV, and C multiplied by the number U cross V, of course, are the same. In the third video, we'll do a logical proof that that is always the case. Another property of the cross product is that if you take a vector and cross it with itself, you always get the 0 vector. This is in contrast with what happens in ordinary arithmetic, where if you multiply a number by itself, you never get a negative number, and you only get 0 when the number itself was 0. Likewise, the dot product of a vector with itself is the square of its length. That's at least 0 and only 0 when U is the 0 vector. So this is something new. We're claiming that under this new cross product situation, if you take a vector and cross it with itself, or a multiple of itself because of what we've just said, you're always going to get 0 for an answer. The 0 vector, that is. Another fact that turns out always to be true is if I add two vectors together and then form the cross product with a third vector, it's always the same as U cross the first vector plus U cross the second vector. As an example, I'm going to let U be the vector 1, 2, 3, V be 4, 0, 1, W will be 2, 6, 7. I'll go ahead and add V and W together by hand. 4 plus 2 is 6, 0 plus 6 is 6, 1 plus 7 is 8, and then we'll calculate these vectors and see if they're equal to each other. Firstly, U cross V plus W, this would be 1, 2, 3, cross product with V plus W is 6, 6, 8. The cross product of 1, 2, 3 with 6, 6, 8 is negative 2, 10, negative 6. To form the right-hand side, I have to form 1, 2, 3 cross 4, 0, 1. Also 1, 2, 3 cross 2, 6, 7 and add them together. U cross V works out to be 2, 11, negative 8, while U cross W ends up being negative 4, negative 1, 2. And then to get the right-hand side of the equation, I have to add these together. 2 plus negative 4 is negative 2. 11 plus negative 1 is 10. And negative 8 plus 2 is negative 6. This is the vector u cross v plus the vector u cross w. It is the right-hand side. This is u cross v plus w, which is the left side, and they both work out to be negative 2, 10, negative 6. So again, this gives supporting evidence to the claim that this is always going to be true, but it doesn't prove that it's always going to be true. In ordinary algebra, because of the commutative and associative laws for multiplication, if you multiply three things together, you can write them down in any one of 6 different orders, as you like. We already know that the vector cross product does not obey u cross v equals v cross u, so it makes a person wonder if there's going to be some trouble now. Is it true or is it false that u cross v cross w is the same vector that you get if you find u cross v first and then cross product that with w? Observe, I haven't changed the order in which the u, v, and w are written down. I'm just grouping the cross product multiplications differently. Let's investigate this. So u cross v as a vector, then cross product with w, comes up to have components 26, negative 8, negative 27. This is not the same as that. Not only that, they are not negatives of each other. The first 2 components of this vector have the same sign, but that one doesn't. There's no way they can be multiples of each other then. Also, if you calculate the lengths of these 2 vectors, you'll find out that they're not the same. So there is no associative law like that. Generally speaking, if you're hoping that this vector and this vector are the same, you are hoping on an unreliable thing. By luck, it might work out that way, but it doesn't have to. If you have 2 vectors, put their initial points at the same place and form the same parallelogram that we do when we're going to add and subtract vectors. If you want to know the area of that parallelogram, you form the cross product of u and v, and then take the magnitude of that vector. We will convince ourselves that this is true in the third video. In three-dimensional space, if you make a shape that's kind of like a rectangular box, but whose sides are parallelograms instead, you call such a thing a parallelepiped. If I have a corner from which vector u takes me to the next corner, vector v takes me to another, and vector w takes me to another, then, as we're going to show in the third video, the volume of such a thing is easy to calculate. You take two of the vectors and cross product them, do the dot product with the other one, and then take the absolute value of the result. Since we could relabel this to be v, that to be w, and that to be v, the order in which these things appear can't matter. The absolute value will take care of any ambiguity, as we'll see. This is the second of 3 videos that I'm going to do about this cross product thing. Hopefully this has been clear enough to understand. I've used a computer program that I wrote to keep the drudgery of the calculations to a minimum. I hope everybody is having a good day. I'll talk to you again soon.